So we have a few goals in this lesson. They're all incredibly important because chemical equations, chemical reactions, as you might guess, forms the backbone of everything we do in chemistry, right? So the goal here is we want to talk about what is a chemical equation, how do we write them down, what is the proper way to write them down, and also what does it mean to balance a chemical equation, or you might hear it referred to as balancing a chemical reaction. What is a balanced reaction? What is an unbalanced reaction? And why is that important? All of these are absolutely critical because everything we do from here on out is going to involve a reaction. All right, so a reaction in general is when you have some atoms or molecules or other substances that come together and react in such a way to rearrange themselves into what we call the products. So the reactants is what we start with at the beginning. The products are what we get at the result of the reaction. Now, the most easy to understand reaction, and one that's very common, is how do we form water, H2O. That's what everyone's familiar with, so that's what we're going to start with. And so let's write this down. All right, so you might think that to bring water together, H2O, you're going to need some hydrogen, and you would be right. You would be correct in guessing that you would need some hydrogen, and you would also need some oxygen, right? But the problem is, I guess I shouldn't say it's not a problem so much as it's a reality. Some of the atoms on the periodic table, they don't come in single atoms, right? We have these ideas in the concept of what we call a diatomic molecule. Some atoms on the periodic table, the gases, some of the gases, do not exist as like single hydrogen atoms floating around. They always bond together in pairs, which we call a molecule of hydrogen or a molecule of oxygen. So normally you might think, well, I need some hydrogen and oxygen, so I'm going to put a plus sign here and I'm going to combine them together. However, hydrogen doesn't exist by itself like this, and oxygen doesn't really exist like this. Always hydrogen exists as H2, two hydrogen atoms bonded to itself, or two atoms bonded to each other, which form a molecule of hydrogen. Same thing with the oxygen. We've already talked about the diatomic molecules. And so when we try to take hydrogen and combine it with oxygen to form water, it has to be H2 plus O2. And that's just because you really don't find atomic hydrogen just floating around. If you did have a container of that, they would quickly form molecules. Now, what do I mean by molecules? These white balls here are what we're calling hydrogen. This is a hydrogen atom, and this is a hydrogen atom. If the hydrogen atom were just floating around like this, then this would be H, and this would be another one. What I'm trying to tell you is they don't exist like that. They always like to bond to one to the other like this, and we're going to talk a lot more about bonding later. You're not expected to understand that now. Hydrogen is going to exist as a molecule with two of these hydrogens bonded together. The yellow stick is representing a force holding them together. We're going to talk about why this happens a lot later. So this hydrogen, H2, is floating around as a pair. They're bonded together. They can bump off the walls of the container and so on, but they're bonded together like this, right? And the same thing is happening with the oxygen. The oxygen molecules they're not individually floating around as individual atoms of oxygen like this. If they ever did, then when they bumped into each other, they would quickly bond. And we're going to talk about later exactly why these things like to bond, but we're not there yet. So just for now, understand that oxygen always forms a molecule with two oxygen atoms bonded together, and the hydrogen always forms a hydrogen molecule as well. So these can be bouncing around in a container, and somehow when they come together, somehow they form water. Now we all know that the chemical formula for water is H2O. So let me write that down. Now before we do anything else, let's see how this could happen. What we're saying is somehow hydrogen molecule comes together and an oxygen molecule comes together, and somehow the atoms which are here and also right here, there's 4 atoms here, somehow it gets rearranged to make water. So let's just see if we can make that happen. Just, you know, these atoms behave like little building toys, right? So let's just go ahead and take this apart. These oxygens come apart. So it's H2O, and we'll put another black stick over here. And essentially, this is the one oxygen atom right here. The hydrogen breaks apart over here and goes right here. And then you can see what happens is it becomes H2O. Now we're going to talk more. We talked a little bit about why it's bent like this, but you get the idea. We pulled this apart and we rearranged it to form something new. Now this is a molecule that's joined together and it behaves as a unit. This water molecule can bounce off the containers and collide with other water molecules and things like this, but it forms its own kind of like complete package that stays together, and it has a certain geometry to it. Okay? There's only one problem. If this is H2O, see, I have a leftover oxygen. Because here there was 2 hydrogens and here there was 2 oxygens, and in order to rearrange it to make water, I have a leftover oxygen. So that is not going to work. This is what we call an unbalanced chemical reaction. It's not balanced because it cannot happen this way. If you notice, how many hydrogen atoms did we start with? 2. How many oxygen atoms did we start with? 2. But over here there's 2 hydrogens, so we have the same number of hydrogens after the reaction's over, but this oxygen, we had 2 of them, now there's only 1 of them, so there's an extra one left over in my hand. So there is an unbalanced number of atoms on both sides. There is a law in physics and chemistry called the law of conservation of mass. That means that everything's composed of atoms, and in a chemical reaction, all that is happening in all chemical reactions is that the atoms are rearranged. So if the atoms are simply rearranged, then if you count up all the atoms before the reaction and after the reaction, you should have the exact same number of atoms. And so that's called the law of conservation of mass. And we don't have the same number of atoms here, so this cannot happen like this. So what we have to do now is learn that this is what we call an unbalanced reaction. We have to learn how to balance this chemical reaction. So let's write down the exact same thing. And this arrow means yield. So this is H2 molecule plus O2 molecule yields something we call H2O. Now, notice that each of these things have subscripts. This is a 2, this is a 2, this is a 2. When you balance a chemical reaction, you cannot change the subscripts that are inside the molecules, because that forms what the molecule is. You can't change that. You can change the coefficients. In other words, we can't alter these things to balance it. The only thing we can do is add coefficients on the front, and you'll understand why we are able to do that in just a second. So let's ask ourselves, we have 2 hydrogen atoms. We have 2 hydrogen atoms, so that's correct. We don't have to make any changes. Here we have 2 oxygen atoms, and we only have 1 oxygen atom here. So in order to fix that, we have 2 oxygens and 1 oxygen. What we can do is put a coefficient in front of the H2O. We're going to say that not only is there 1 water molecule on the right, the coefficient in front means that there's now 2 water molecules on the right. So if we use this as a starting point, let's write down the reaction again. H2 plus O2 yields 2 molecules of H2O. Now let's ask ourselves, is this reaction balanced? Okay, so there's 2 oxygen atoms, and since there's 2 water molecules and there's a 1 right here, that means there's actually 2 oxygens that match this, so that's good. But the problem now is that you see we have 2 water molecules, each one has 2 hydrogens, so there's 2 times 2, which is 4 hydrogens on the right. So you multiply the coefficient times the subscript. There's 2 hydrogen atoms here, but there's only, 4. There's only 4 on the right, but there's only 2 on the left. How do I fix that? Because I'm allowed to add coefficients, I'm going to put a 2 right here. And I ask myself, is this now balanced? We start over again. Okay, 2 times 2 is 4. There's 4 hydrogen atoms on the left. 2 times 2 is 4. There's 4 hydrogen atoms on the right. That's correct. Law of conservation of mass, we have the same number of hydrogen atoms on the left and the right. Then we say there's 2 oxygen atoms on the left. How many do we have on the right? There's a 1 here, so 2 times 1 is 2. There's 2 oxygens, so that balances. So by adding coefficients in front of the reactants and the products in the reaction, we can balance the chemical reaction. This is impossible. I didn't tell you it when I wrote it down because I didn't want to like gum up the discussion. This is impossible because when you do this, you have a leftover oxygen, and that's not going to happen. It's not going to just have a leftover oxygen that's going to float away. What's going to happen is instead, these things are going to happen in a different ratio than what we wrote down here. What it means is that instead of this happening, what really happens when we form water is the following. 2 molecules of hydrogen, H2 gas, combine with 1 molecule of oxygen, O2 gas, which forms 2 molecules of water. So let's demonstrate how that could possibly work. So what I'm going to do is I'm going to disassemble what I have from before, put it back together, and we're going to see visually how this might work if I can put it together real quick. So here on the left, I no longer have a single hydrogen molecule, I have 2 of them. So that's what the 2 represents. The coefficient of the 2 means I now have 2 of these hydrogen molecules. Each molecule has 2 hydrogen atoms bonded together. So this is what I have right here. And then this single, there's a 1 right here, this single oxygen molecule is O2, and this is what really combines together. So if we rearrange all of the atoms that are here into water, we should have not 1, but 2 water molecules. So what I'm going to do is put these down. I want you to remember with me, because you got to try to remember. I'm going to take this apart, and I'm going to put one of these oxygens down. I'm going to take, now I've taken that and I put it downstairs. Now I'm going to break apart this hydrogen molecule, and I'm going to, see, these were bonded together. I took the stick away, but you get the idea. They were bonded together. There's the single, the O2, I broke it apart. I put the other one down on the counter, and what's going to happen is this one is going to make a single water molecule. But now this reaction is telling me that I should actually make 2 water molecules. So let me put that aside, and this is what I have left over. I have the other oxygen atom that was bonded that I broke apart, and I have the other hydrogen molecule. So I'm going to take that apart, and all I'm going to do is put these sticks in place, and I think you see what's going to happen. So now I have everything in place from before. I'm going to put this in place like this. I'm going to put this in place like this. And here's one water molecule, and here is the other water molecule. So it is not true that you can just take hydrogen gas, 1 molecule of it, and 1 molecule of oxygen to make 1 molecule of water. It doesn't work. The masses of the atoms don't add up. Here is what actually happens. 2 hydrogen molecules combine with 1 oxygen molecule to make not 1, but 2 of the water molecules. So the coefficients, a lot of students, they learn how to balance equations, but they don't really know what the coefficients mean. It is literally telling you the ratio of what these things are combining in. It is 2 hydrogen molecules combining with 1 oxygen molecule to give me 2 molecules of water, and there's nothing left over because, why? I have 4 hydrogen atoms, 2 oxygen atoms, 2 oxygen atoms, and this is what we call a balanced chemical reaction. All right, same atoms on the left and the right. We do not change any subscripts anywhere. We only can change the coefficients, and that's all we want to be able to do. And we want the lowest whole number coefficients we can get. Remember when you learned back in 3rd or 4th grade how to simplify a fraction, right? You know that 5/10, for instance, 5 slices out of 10 slices of a pizza, that's half a pizza. You know that, right? 5/10 is the same thing as 1/2, but we never say 5/10, we just say 1/2. We want the lowest whole numbers for the fractions. So for the reactions, we want the lowest whole numbers as well, 2, 1, 2. You can't simplify these numbers anymore by dividing by anything, so we just leave it alone. All right, now that we spent some time talking about the first one, the rest of these are going to go a little faster. It always takes longer with the first. So what I want to do for the next one, I think I want to solve it. I think I want to solve it 2 different ways, or maybe no, that's the next one. Sorry about that. We'll do the next one 2 different ways. Let's go ahead and write down the next equation. So let's talk about CH4 plus O2, and that's going to yield CO2 plus H2O. Now this is a more complicated reaction, mostly because it's not quite as familiar. We all know that hydrogen plus oxygen gives us water. That's why I started with this. Now this is something called methane, combining with oxygen, burning with oxygen, and it gives CO2, which is carbon dioxide, and it also gives H2O, which is water. Now, we're going to talk a lot more about types of chemical reactions in a later lesson, but I can tell you right now that when most things burn, and that's what's happening here, we're combining with oxygen, the methane is a fuel, and it's burning, right? When most things burn, it almost always forms CO2, carbon dioxide, plus H2O. And that's because, we're going to learn later why, but CO2, carbon dioxide, and water, H2O, they're very, very stable molecules. And that means when the burning happens and everything recombines, they always try to go to the most stable configuration. CO2 and H2O are very, very stable. We're going to talk a lot more about why later. So when things burn, it almost always makes CO2 and H2O, almost always. Now let's ask ourselves, is this a chemical reaction? So what we do is we start by looking at the first molecule we run across. We have CH4. We have one carbon atom, and then on the left-hand side, on the right-hand side, we again have CO2 with only one carbon atom. So the carbon atoms are balanced, right? Then we look at the hydrogens. We have 4 hydrogens. We look on the right-hand side, we only have 2 hydrogens, so immediately these are unbalanced. This cannot happen the way it's written, because if it combined this way and you only had 2 hydrogens used over here, where would the other 2 of them go? They're not just going to float away. When a reaction happens, everything is going to be rearranged and accounted for on the right-hand side of the arrow. If you can't account for it, it's not going to happen like that. So what we need to do is rewrite the reaction. CH4 plus O2 yields CO2 plus H2O. All right? Now, we already said that the carbon was balanced, so we don't do anything related to the carbon, but we said we have 4 hydrogens here and we only had 2 here. How do we fix that? We need to put a 2 as a coefficient in front of the water molecule, because now 2 times 2 means there's 4 hydrogens on the right and there's 4 hydrogens on the left. There's still 1 carbon on the left, still 1 carbon on the right, so that's all correct. Now then we ask ourselves, how many oxygens do we have? On the right, we have 2 oxygens in the carbon dioxide, but we have 2 molecules and there's a 1 here, so 2 times 1 is 2. We have 2 oxygens and 2 more oxygens for a total of 4 oxygens, and we only have 2 here. So let me rewrite this again. CH4 plus O2 yields CO2 plus 2H2O. All I'm doing is rewriting what we've done. I'm going to tell you why I'm doing it this way in a minute, but let's ask ourselves again. Let's go a little faster. 1 carbon, 4 hydrogens, 4 hydrogens, 2 oxygens. Here's 2 and 2 more. There's 4. How do I fix it? I'm going to put a 2 in front. Now there's 4 oxygens. 2 from here means 4 oxygens. Everything is balanced. 1 carbon, 4 hydrogens, 4 hydrogens, 4 oxygens. 2 plus 2 is 4 oxygens. This is a balanced chemical reaction. All right? Now, let me start to give you a little bit of pointers, because these reactions I'm writing down are pretty easy to do. All right? Now, the first time you learn it, everything seems a little hard, but you'll find out that these are fairly easy reactions to balance. We're going to get to much harder ones in a minute. But I want you to not, when you do your homework, to not write down the reaction and start erasing and then putting new numbers and erasing and putting new numbers. That is how to make this much harder than it has to be. Notice that I wrote the reaction down, and then I wrote it down again before I made any changes. And I put a 2 here, and then I wrote it down again, copying this 2, and then I made another change. It would be very tempting to put the 2 right here, but the problem is, if you start modifying and making more than one change to every reaction you write, you're going to end up having to erase and write down a new number on top, and then that's going to cause you to erase something else and write down a new number, and you can kind of go and spiral out of control, erasing and recopying numbers over and over again. So please write the reaction multiple times like I'm doing it. I'm not trying to waste your time. This is the best way to do it. You need to write the reaction multiple times, otherwise you will get stuck. When I give you a more complicated reaction, you'll be erasing so many times you'll be confusing yourself, okay? Now, this is the balanced reaction. The number of atoms are the same on the left and on the right. Now, we can actually add the states of matter to chemical reactions, and we're going to do that here. The way you would write that down is this CH4, this methane, in this reaction is a gas. So we use parentheses with a letter G to tell the reader that this is methane gas. It's not solid methane, frozen methane, or something like that, right? And then we're adding that to 2 molecules of oxygen, which again is a gas. So we put parentheses with a G. And then this arrow here means it yields CO2, which, as you probably know, is a gas. And then 2 molecules of H2O, which is a gas. Notice I've copied the thing down. 1 molecule of this, 2 molecules of this, 1 molecule of this, and 2 molecules of this. All I did was add parentheses to indicate to the reader that these are gases, right? So you're going to see this as we write chemical reactions down more. What we generally see is that G means gas. Can you guess what S means? That's solid. right? If I put an S here, it would be solid oxygen, right? Well, that's pretty hard to come by, but you could put it there, right? Right? Liquid would be L. And the one that gives students the most trouble in the beginning is AQ, which means aqueous. Aqueous. All right, AQ, aqueous. Aqueous means that it is in a solution of water, right? Aqueous means solution of water. So if I put sodium chloride, NaCl, parentheses aqueous, that would mean salt dissolved in water. A lot of chemistry happens in a water solution. Think about your body. Your body is mostly water by weight, right? The chemical reactions in your cells, they're all happening in a solution of water. We're bags of water, basically, is what all life is. We're bags of water with chemical reactions happening inside. So we use aqueous because a lot of reactions in real life, in terms of chemistry and biochemistry, actually do happen in an aqueous solution of salt water, or in a solution of water. So when you see AQ, it just means, oh, it's dissolved in some water, and that's the medium in which it's reacting in, some beaker full of water or something like this. Okay? So going forward, I will try to write the states of matter in the reaction. If I forget, don't get too mad at me. I'm human also. I may drop it sometimes, but in general, you should write them when you think about it, as that is the best thing to do. All right, next reaction we're going to balance is a little more complicated. I told you we're going to get a little more complex as we go. What about cobalt, CO2O3? And that is a solid, so I'll put S in parentheses. And we're going to combine that with carbon, another solid, right? And that's going to yield CO, that's cobalt, which is a solid, and then plus CO2, gas. Now, I have left out a lot here. In introductory chemistry, you don't really know how these reactions actually take place. Are we adding heat to make the reaction take place? Are we adding electricity? Are we shaking it up in a test tube? Are we agitating it? Are we stirring it? Or is it spontaneous? There's lots of questions that you should have now. For now, hold those questions. We talk about how reactions proceed a little bit later. For now, just know that if you were to react this with this, and if it were to form this and this, would this be a balanced chemical reaction? And if not, how do we fix it? I can tell you right now it's not a balanced chemical reaction, so let's first start by rewriting the thing. We don't want to change what we have here because we want to have a clean version of the problem to work with. So CO2O3, and what I'm going to do when I balance the thing is I'm going to drop all the parentheses with the states, and then in the final answer I'll try to remember to write them back in because it's just too much writing if you write them over and over again. So plus carbon, and then we have the CO right here, and then the CO2. See how much cleaner this looks in order to balance it. All right, now, there's a couple of rules of thumb I need to bring to your attention. The first rule of thumb is when you balance chemical reactions, usually, these are just rules of thumb, they're just like helpful hints, okay? Usually, you try to work with the more complicated molecules that you have first. Anything single, like this single carbon atom and this cobalt atom, you generally leave those for the end because it's very easy to balance single atoms. It doesn't affect anything else. But you see, if I put a number 2 or a number 3 in front of here, it's going to affect the carbons and the oxygens. So you want to take care of that stuff first and then leave anything single for later in general. There's some exceptions to that, all right? Like oxygen, a lot of times we want to leave at the end no matter what, but sometimes we change our minds on that too. So there is no right way. I'm just giving you some rules of thumb. So when you go through this, you first say, all right, there's 2 cobalts here. On the right-hand side, there's only 1 cobalt. So you could say, I'm going to fix that. I have 2 of them here. I can put a 2 right here to fix it. And that's fine. You can absolutely do that. But I'm telling you that it's going to make a little bit easier time going, less erasing, to just save the cobalt for the end. Because if I write a number 2 here, I may have to change that number later. If I have to put a coefficient here, it's going to change everything, and then I'll have to erase that anyway. So let's skip the cobalt for now, even though it would be simple to fix, and let's instead look at the oxygen. This is the most complicated kind of like substance we have here, more complicated than these anyway. So I have 3 oxygens, right? Over here I have 2 oxygens. How do I balance that? I can't multiply this by a whole number and balance it with this. So this is an example of when I'm going to actually work this problem 2 different ways. So there's that. But also, I'm trying to show you the freedom. In all of these previous problems, we did one thing at a time, and usually that is what I want you to do. But in this case, I can't really multiply by a whole number, by any one thing to fix the oxygen. The carbon is already balanced, and the cobalt I could fix, but that's not going to fix the oxygen problem. So what I'm going to do here is I'm going to put a 2 in front of this, and at the same time I'm going to put a 3 in front of this. This is a rare case when I do two things at once, because I cannot write a single number down that will fix the reaction, right? But now if I put a 3 here, how many oxygens do I have? 3 times 2 is 6, 6 oxygens. 2 times 3 is 6, 6 oxygens. So by putting a 2 here, what was over here, and the 3, putting it over here, 3 times 2 is 6, I've balanced the oxygens. So now let's rewrite what we have. We have 2 CO2, O, whoops, not a capital O, it's a lowercase o, 3 plus C yields CO plus 3CO2, like this. And so I have the 2 here and the 3 here. All right, so now I have balanced the oxygens. There's 6, there's 6. The carbons are unbalanced now, and the cobalts are unbalanced. So notice what we have here. We have 4 cobalts. We're done with the more complicated element, so we have 4 cobalts, so I'll just put a 4 here to try to balance that. Now let's rewrite what we have. We have 2 CO2O3 plus carbon is 4 cobalt, 3 CO2. So let's go back from the top. We have 4 cobalt, 6 oxygen, 6 oxygen, 1 carbon, 3 carbon. How do I fix it? Well, since carbon's by itself, I'll just put the 3 here and it doesn't affect anything else, and it's correct. So 4 cobalt, 6 oxygen, 3 carbon, 3 carbon, and that's it. This is the balanced reaction. This is the answer. Now, I told you that I would try to remember to write down the states, and so this was a solid, this was a solid, this was a solid, and this was a gas. Now, I may forget that. In general, though, you should try to write the states of matter in your reaction. I don't particularly like to do it as I'm balancing it because it makes it hard to keep track of, okay? So what I'm going to do is we solve this one in what I think is a very good way. I'm going to leave this here. We're going to solve the rest of the problems in this lesson, and then we're going to come back and I'm going to solve this a different way because I like you to see different ways of doing it. And I want you to have all of the knowledge I have. So for now, I don't want to gum up the discussion. Let's continue on, get some more practice, come back to this, and I'll show you a slightly different way to tackle it, but you will get exactly the same answer as what we got here. All right. Let's move on to our next reaction. It's not too hard. Let's take a look at butane, which is C4H10. That's gas. We're going to combine that with oxygen gas. Notice it's O2 because oxygen is diatomic. And that yields CO2 plus H2O, both gases. Told you that general, when things combust, they make CO2 and H2O. There are exceptions. Of course, there's always exceptions. But this is a totally different thing that was combusting before. I mean, this is totally different. It yields CO2 and H2O. This is a totally different thing, but it still yields CO2 and H2O. So I already know that this thing is completely unbalanced. So let's just save ourselves some time and just rewrite it again. And we'll strip away C4H10. And then we will write O2. And then we will have CO2 plus H2O. All right, so in general, we don't want to mess with the oxygen here. We're going to leave that for later because it's off by itself. We want to work on the more complicated things. We have 4 carbons here, and so we look over here, where's the carbon? It's right here. There's only 1 of them here, and there's 4 of them here, so I need to fix that. So how am I going to fix that? I'm going to put a 4 as a coefficient in front of this. I know it's not balanced still, so let me rewrite it. C4, H10, O2, 4, CO2, H2O. All right, now let's go back from the top. 4 carbons, 10 hydrogens. The only hydrogen I have over here is right here, and there's only 2 of them. So how do I make 10 to match what I have over here? I have to put a coefficient of 5 in front of this. So we'll check it. 4 carbons, 10 hydrogens, 10 hydrogens. Now there's 2 oxygens, and there's 8 here because there's 2 times 4 is 8. So plus there's more from over here, so it's actually even more complicated. So let's just write down what we have here, and we'll change the coefficient. So C4H10, then we have O2, then we have 4CO, carbon dioxide, and we have 5H2O. All right, from the top, 4 carbons, 10 hydrogens, 5 times 2, that's 10 hydrogens. Now, I don't have enough oxygen. How many do I have right here? Well, the oxygen from right here is there's 8 of those. There's 8. 2 times 4 is 8 oxygens. And then from right here, there's 5. 5 times 1 is 5. And then all together, 8 plus 5 is 13 oxygens. So there's 13 oxygens on the right. All I have to work with is this position here. There's no oxygen anywhere else, so I can only change what's in front of this. But 2 times any number I can think of, it never equals 13. If the answer were 12 over here, then I could put a 6. 2 times 6 is 12, and it balances. So this is why we need to take the training wheels off. The earlier problems were a little bit simpler. This is a little more complicated. It actually shouldn't be complicated, but it is for a lot of students. So you have to work with fractions. Remember fractions? The thing people say, why do I ever need fractions? This is a great example of why you need fractions. You have 13 oxygens over here. You need to put a number in here that when it multiplies by 2 gives you 13, and you are allowed to use fractions. I haven't told you that until this point, but you are. What can you put over here? You can put the fraction 13 halves. You might say, number 1, how does this work? And number 2, how does this make 13? Well, if I take the coefficient of 13 and I multiply it, or 13 halves, I should say, and I multiply by this, 2, that's what we always do, we multiply it, but 2 is 2 over 1. These cancel, and I get 13. So by multiplying these, that's the same thing I'm always doing. I'm multiplying, 3 carbons, 3 times 1, 4 cobalts, 2 times 2 is 4. I'm doing the same thing, 13 halves times 2, gives me 13 oxygens, which balances 13 oxygens. So that's it. Now, you might say, I've never seen a chemical reaction with a fraction here. This is a fraction of an oxygen molecule, right? If the number were 5 here, it'd be 5 oxygen molecules. If the number were 10, it'd be 10 oxygen molecules. But I'm telling you 13 halves is a fraction, some non-whole number. So what we want to do for our chemical reactions, you can use fractions anywhere you want, but after you balance everything with the fractions, then you have to multiply through the chemical reaction to clear all the fractions away, right? And if you do that, that's fine, but you have to multiply every single term by the same number, right? It's just like balancing a fraction in math. You can multiply the numerator and the denominator by anything you want. You get the same fraction. An equation in algebra with an equal sign, you can multiply the left and the right by 5 or 10 or anything you want. You can do the same thing with chemical reactions, chemical equations. That's why they're called an equation. So what I'm going to do here, since there is a 2 on the bottom, I'm going to multiply by 2. And what does that do? Right? Well, if I multiply this by 2, it's going to be 2CH4 or C4H10. Right? And if I multiply this by 2, then it's going to be exactly what we have right here. I just showed you how it cancels, and so you just get 13. So when we multiply by 2 here, we're going to get 13 oxygen molecules. If I multiply this by 2, 4 times 2 is 8, so it's 8 CO2 molecules. And if I multiply this by 2, 5 times 2 is 10, and that's 10 water molecules. And then I said I would try to remember to add the states. Gas, 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 so this would be gas. This would be gas. I never leave enough room. This would be gas, and this will be gas. And let me check my answer. So I check my answer. 2 C4H10, 13 O2s, 8 CO2s, and 10 H2Os. Now we're claiming that this is balanced. Now let's check it, because when we get to the final answer with whole numbers, we should have a balanced chemical reaction. So 2 times 4 is 8 carbons, and over here we have 8 carbons. That's good. 2 times 10 is 20 hydrogens. That means 10 times 2 here is 20 hydrogens. That is balanced. 13 times 2 is actually 26 oxygen atoms. And then from here, you're going to have 16 from here, because 8 times 2 is 16. And then you're going to have 10 times 1 is 10 from here. And what did we say? 13 times 2 is 26. When we add these together, we're going to get 26 oxygen atoms. So we have the same amount of carbon on the left and the right. We have the same number of hydrogen on the left and the right. We have the same number of oxygen on the left and the right. This equation is balanced. And it is in lowest ratio, right? There's nothing I can divide by. This is an even number. These are even numbers, but this one is not. So I cannot divide through because just like I'm allowed to multiply through, I could divide everything by the same number if I wish, or multiply by 1/2, but these are the smallest whole numbers that will balance this chemical reaction. So from the top, from this example, which is a little more complex, I understand, but you need to be okay with the idea of using fractions to balance chemical reactions because it saves a lot of time. When we got down to the first part of it, we said we had 4 carbons, so we added the 4 here, and that balanced the carbons. Now we rewrote the equation here, and we said, well, we had 10 hydrogens, so we balanced that by putting the 5, 10 hydrogen. We were good. Then we got down to the point where we said, well, wait a minute, here we had 8 oxygens. Here we had 5 more, which is 13 oxygens. There's no whole number I can multiply here times 2 to give me 13. So I have to resort to fractions. 13 halves times 2, that does give me 13. I use the fraction. This is balanced, but we never want to see fractions in our final answer. So we multiply through term by term by any common number we wish. We multiply by 2 to clear the bottom. Multiply this by 2 to get this. 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 And this is the balanced reaction in terms of whole numbers. All right? Now that we have done the introduction of using fractions to balance a chemical reaction or chemical equation, I want to go back to the previous problem, this one. I want to do it in a different way. We've already solved this problem. Notice in step number 1, it was I broke my own rule. I said I'm going to put a 2 here and a 3 here at the same time. I never do I never do 2 things at once, really. But I broke my own rule here because of the oxygens. 2 times 3 is 6 oxygens, 3 times 2 is 6 oxygens, and then I balance the reaction. Let me start over and say CO2O3 plus carbon, CO and CO2. So let's start over and let's see if we can find a better way or a different way to do it. We want to leave the cobalt for last because it's by itself. All right, we have 3 oxygens. What can we multiply here to give me 3? Well, there is no whole number. That's why we did what we did before. However, if I have 3 oxygens here, I can still balance this by writing the fraction 3/2 down right here. Because if I take 3/2 and multiply it by 2, which is 2 over 1, then I get 6 on the top and 2 on the bottom, which is 3. And that's 3 oxygens to balance this one. So I used, instead of doing 2 things at once, which I generally don't like to do, now that you know you can use fractions to balance chemical equations, it's very empowering because I know I need 3 oxygens. I'm going to use a fraction to give me my 3 oxygens. Okay, so that's balanced. Let's continue. So let me write this again. Let me write the whole thing down again. So CO2O3 plus carbon, CO, 3/2, CO2. So I have 2 cobalts. I only have 1 of them here. So I'm going to fix that by writing a 2 right here. Let's write it down again. CO2O3 carbon yields 2 CO plus 3/2 CO2. So let's check it again. 2 cobalts, 3 oxygens. The 3/2 times the 2 does give us 3 oxygens. And I have 1 carbon. How many carbons do I have here? Well, I have a subscript of a 1, so I have 3/2 of a carbon. How do I fix it with a fraction? Well, I can just put 3/2 here. I know it's ugly, right? It's ugly because it has fractions, but there's 3/2 carbon. I can fix it with 3/2 carbon. Now the thing is completely balanced. 2 cobalts, 3 oxygens, 3/2 carbon, 3/2 carbon. It's balanced, but we don't like to leave it like this. We're going to multiply by what? The denominator here is a common number, 2. So when I take the first thing, it's going to be 2 CO2O3 multiplied by 2. When I multiply this by 2, the denominator cancels, and so it's going to be 3 carbons. Multiply this by 2, it's going to be 4 cobalts. And multiply this by 2, I'm going to have a 3 left behind, CO2, because the denominator cancels. Now, what do I have here? 2 CO2, 2 cobalt oxides, I have 2 of those here. I have 3 carbons in this answer, 3 carbons in this answer, 4 cobalts here, 4 cobalts, 3 CO2s, 3 CO2s, exactly the same answer. Now, just like when you solve an equation, you are allowed to do what you want as long as you follow the rules. Same thing with balancing chemical reactions. If you love whole numbers, just deal with whole numbers. It's fine, but you might have to get to some pretty big numbers before it's balanced sometimes. But if you don't want to deal with that business, you can always use fractions. And that's why one reason why we learn fractions is just before we actually write the final answer down, we clear any denominators out of the fractions by multiplying every term by the same number, just like we can multiply equations by the same number. All right, we are almost done. I have 2 fun little problems here. These are going to be very, very fast, so let's just crank through them here. True or false? This is true or false. We balance chemical equations because of the law of conservation of energy. Is that true or false? That is false. Right? We learned about the law of conservation of energy. We talked a little bit about it before. We'll talk a lot more about it later. That has to do with balancing energy. The reason we balance chemical reactions is to balance the number of atoms on the left and the right. That's the law of conservation of mass, not energy. So this is false. It's because of the law of conservation of mass that we balance equations. Problem number 2. If I'm given this reaction, 2 molecules of O3 yielding 3 molecules of O2, true or false? The mass of the O2 on the right will equal the mass of the O3 as the reaction completes. Will the mass, basically the mass balance? And the answer is yes, the mass has always balanced. This is true. Any chemical reaction has to balance, right? Because law of conservation of mass is always true. How many oxygen atoms do you have here? 2 times 3 is 6, and 3 times 2 is 6. So even though this one is grouped as O3 molecules, and this one is grouped as O2 molecules, the total number of atoms is the same, so the mass on the left and the right as the reaction proceeds is not going to change overall. So the mass of O2 will equal the mass of O3 when you add everything together, true. Right? All right, next question. Given H2O is a liquid, yielding or breaking down into H2 gas plus O2 gas, can I balance this equation by simply adding a 2 as a subscript under the oxygen? And so you ask yourself, it's a little trick question. You say, well, I have 2 hydrogens, 2 hydrogens. I have 2 oxygens, 2 oxygens. It's balanced. But the problem is you cannot balance a chemical reaction by changing the subscripts. Look back. Did we ever change any of these subscripts? Never. Did we ever change any of these subscripts? Never. All we were allowed to do was put numbers in front. The number of molecules participating we can change, but we cannot change the subscripts because that changes what the molecule is. It changes the identity of the molecule. And so given this, can we balance it by simply putting a 2 right here? The answer is no, so false. You cannot balance it using this method here. Now, the very final problem that we're going to do today is, this is a generic problem. I have a box with these molecules. Some are called A atoms bonded together like this, and B atoms floating around. And the blue one here, the blue ones are B and the red ones are A. What would be this reaction? Well, let's think about it. In the left-hand side, this is as the reaction completes, we have 2 A atoms together. So we have A2, okay? And then we're going to add this to B atoms, but they're not bonded together, so B atoms are just by itself. But how many do we have? We have actually 1, 2, 3, 4 molecules of the A2 atom. These are generic molecules, right? We have 1, 2, 3, 4 of those molecules, and we have 1, 2, 3, 4 of the B atoms, like this. And what does it kind of form on the right-hand side, right? Well, what does it form? It forms a new molecule where it's A2B. A2B. This is like H2O, right? A2B. And this is like a single unit. How many of these units do we have? 1, 2, 3, 4 of those. So there's a 4 in front of there. So what we figured out is that 4 of these molecules called A2 combine with 4 of these individual atoms called B to yield 4 groupings of molecules of this thing called A2B. Now, as I mentioned before, we can multiply reactions by any number we wish, as long as we multiply the left and the right. Just like in algebra, you multiply an equation, left and right-hand side of the equal sign, multiply whatever you want. But in algebra, you can also divide by anything you want, because dividing is the same as like multiplying by a half or multiplying by a third. When you divide, it's the same as multiplying by a fraction, right? So here we have a 4, and a 4, and that's okay. We could leave it like that, but we can also just divide by 4, which is the same thing as multiplying every term by 1/4. So if we divide by 4 here, we just get A2 here. If we divide by 4 here, we get B. And if we divide here by 4, we get A2B. So again, you can think of it as dividing by 4. You can think of it as multiplying by 1/4, give me 1. Multiply by 1/4, give me 1. Multiply by 1/4, give me 1. This is the proper balanced chemical reaction, because a balanced chemical reaction should have the lowest ratio of whole numbers in there. I mean, I can multiply this thing by anything I want. I can make the numbers huge, but we want the lowest whole number ratio of what's combining together. So because we could divide by a common number, that's what we do, just like simplifying a fraction. 5/10 is the same as 1/2. We divide top and bottom by 5, right? And we get a new fraction, but it means the same as the old fraction. We divide every term here by the same number, we get a new equation, but it's the same ratio. Instead of 4 of these molecules combining with 4 of these, yielding 4 of these, we just simply say, it's simpler to say, one of these combines with one of these to give us one of these. And this is the simplest way of expressing that. So here we have gone through one of the most important things in all of chemistry. It really was a breakthrough in human deduction to figure out how this works. Because before the advent of chemistry, before anyone knew about atoms, there was just a seemingly infinite number of substances out there. Water, clouds look different than water, even though now we know they're the same thing. They're just liquid versus vapor, right? Ice looks different than water, right? And then you have all the organic substances like, anything alive that looks totally different than everything else. And, metals look different. And then when you combine them, the substances, rust looks different than iron. But now we know that's iron combining with the oxygen to make the rust, So before, it looked like there were just trillions and trillions and trillions of unique substances. What chemistry figured out is that everything is made of about 100 different elements. Periodic table has a little bit more than 100, but the last dozen or more are really very highly unstable. So in nature, about 100 elements comprises everything, but they are joined together in different ratios. And when we take certain substances and combine them together, they like to rearrange their atoms to make new products, which will have new properties, okay? So that's why things look like there's so many different varieties, because it's when the atoms rearrange, they appear to be very different, even though they're made of the same stuff. For instance, we started this whole lesson by talking about water. You know that water at room temperature is a liquid. You can drink it, you can spray it in your lawn, you can pour it, you know what a liquid is, right? But what is comprised of the inside of this water is really the hydrogen and the oxygen at room temperature. This is a gas, it's flammable gas. This is oxygen, it's also a gas. It likes to combine with the hydrogen, right? But water is not flammable. It doesn't have the same properties. It's also not a gas at room temperature. Well, it can be, but it usually at room temperature is a liquid, right? So the properties of this and the properties of this are totally different than this. So when you take the different atoms and you combine them, the properties of the final substance is totally different. So that's why for thousands of years people thought everything was just different. There was just thousands and trillions and trillions and trillions of unique substances in the world. Now we know there's really only about 100 different things. And those 100 different things combine. Chemical reactions are how they combine and rearrange to form new things. And the balancing of the chemical reaction, which is what we learned here, is because of the law of conservation of mass, because those building blocks, they cannot be created, they cannot be destroyed, they can only be rearranged. So in the left-hand side and the right-hand side of the reaction, you must be able to account for all of it, and that's why we balance these reactions. Now, solve these yourself. Follow me on. We have a lot more practice to do with balancing chemical reactions, so follow me on. We'll conquer that right now. Learn anything at mathandscience.com.